Hello, I'm Professor Congleton, and this is Econ 701, Advanced Microtheory. What I'm going to do today is to provide a little overview for the midterm, and I'm just going to go through the high spots to kind of help remind you of what we've covered so far in the semester. So basically we've got consumer theory, theory of the firm, and equilibrium prices. So in terms of the economic content of the course, basically we've just gone through what the same topics you might have covered in principles and intermediate micro, and if you have another more advanced micro course towards the end of your career as an undergraduate, everybody covers these three topics. So what we've done a little differently than probably most of you have had before, especially those of you who have had more or less geometric-based versions of those courses, is we've tried to develop kind of a mathematical background for those diagrams that you learned when you were an undergraduate. And basically been able to show that there are sort of new things, some more general things you can say, which are completely consistent with those undergraduate diagrams, based on the mathematics. And the mathematics kind of helps to inform the way you interpret those diagrams. So the diagrams are so useful. Some ways they're more useful than the math, but without the math, the diagrams are far less useful. So in order to create this sort of mathematical background, we've looked at a few series of tools. So we had unconstrained optimization, which would be something like you have some function y equals f of x, dy dx equals df dx equals 0 at x star. And we've had something called strictly concave functions, which means that the effect of a change in x on the slope of the f function is one that is diminishing with x. It's a downward sloping slope function. In terms of economics, it's a downward sloping marginal utility or marginal benefit curve. We've also looked at constrained optimization. The Lagrange method. Which looks like this. You have create a Lagrange function, and there is a function, say, g of x, which is the objective function. And we have some kind of constraint and we take that constraint and we put it in a form equals 0. So there are two parts to that, and then we multiply that constraint function by this term lambda. Okay, of course, it doesn't have to be lambda, but that's the convention. So we use that to characterize two types of situations. One is the consumer choice setting, where the consumer is trying to maximize utility across more than one good. And we took a look at production using that same kind of technology. And the Lagrange approach is most useful when you're dealing with concrete functional forms, because then you have a chance to kind of work through all the order conditions and actually solve for a relationship that's also a concrete function. So it has a sense of kind of looking really precise. We also used what I call the substitution method. And that involved taking the constraint and substituting it into the function in some sense. So we would have something like f of g of f of x, something like that, as the objective function, and the constraint would be embedded in the function in the form of f of x. Now, that substitution process makes sense because all of our functions have positive first derivatives. Things are goods in these models. They're desirable. They add to the value of the thing, the activity, or what have you, for the individual or firm. And so we know that if there's a constraint that's kind of an upper bound on what you can access, then all the actions going to be along the constraint. We'll be looking for tangent points along those constraints, for example. And that means when you do the substitution of the constraint, if you just kind of evaluate the function along that constraint, you're going to find the optimum. Okay. If the constraint was irrelevant, then this technique would not work, but that's also generally true of the Lagrange. Okay. So even though Lagrange conceptually could, I suppose, capture things away from the constraint, it doesn't. So we used the substitution method a couple times. We used it when we were looking at firms confronting downward sloping demand curves and trying to make output decisions that would affect prices. We found it useful to take the demand function and calculate the inverse function. So instead of going from prices into quantities, we went from quantities into prices. And that way we could just substitute that relationship into the revenue function and make the revenue function a function of Q instead of P and Q. And that greatly facilitated the solution to those problems. We also used it in abstract settings like the one I've kind of alluded to there, where for one reason or another we have some abstract functions that we're working with. We know something about the shape of those functions, but we don't know their particular concrete functional form. And we can use this technique sometimes to simplify the calculus and algebra. So we've spent most of the time in class going through applied examples of these mathematical techniques, and we use them in the lecture for a particular reason. Namely that we are assuming that individuals are rational in the sense that they maximize something. Right? They maximize utility, substitute as a constraint, they maximize net benefits, they maximize profits, they maximize output for a given expenditure on inputs. So we use the maximization idea as a kind of characterization of rational decision making in particular kinds of choice settings where maximization makes sense. And given that, the implications that we tease out of the calculus of maximization allow us to say something about the way, about the manner in which people will behave. Right. So the point of all this mathematics is not strictly speaking mathematical, but rather the implications that the optimization process has for the types of behavior we'd expect to observe if people are behaving in a more or less rational way in the choice settings that we model. Now, we haven't developed any evidence in class to support the fact that these models work, but you can rest assured that these models actually do work pretty well, and in a normal microeconomic environment, they often account for 50% of the variation in a person's behavior, expenditure patterns, production and outputs, and so forth, and in the equilibrium prices. which is pretty good if you think of it. Okay, these are just very simple models, and they're able to shed light on just thousands and thousands of different markets without really much more elaboration. So, in other words, these models are pulling out something that's really essential, something that's common to all those different kinds of decisions that we see in markets. And as a consequence, we can use that as kind of the core, the foundation for our understanding of how markets work. Now we can do a little better if we go into a particular market and try to focus in on particular details of that situation, that context that people are making decisions in, that kind of extend the neoclassical frames that we've developed here, which is just the core model. And in that way, kind of improve the fit of the models, improve the explanatory power, and improve our understanding of the markets on specific markets of work. But in many of those cases, we need a lot of specific detail about the choice settings, and what's powerful about these models is simply that we don't. That you can get a good start at understanding how these situations work simply by using very general ideas about decision making. We use these two models in the mathematics to talk about market prices. So the idea of market clearing prices has been around for a while. You can see traces of it as far back as Aristotle, 350 BC. Okay, but the modern formulation of it basically occurred with Adam Smith's famous work, The Wealth of Nations, but also with the marginal revolution in the 1870s and 1880s as those ideas kind of developed into what gradually became the classical economics. So what I'm going to do next is just to kind of refresh your memory about how some of these tools can be used. I'm not going to do a lot of derivations here. I'm just going to kind of remind you of the kinds of things we were working on and how to use some of these techniques in the two of the problems. On the midterm, there will be problems in each of these sections of part one of the course. Truthfully, the exam will, to you, feel like it's 80 or 90% math. Okay? Which will be trying to get you, I'll be trying to get you to engage these choice settings with this tool set and try to figure out what's going on in terms of what can we predict about the behavior of the individuals in these circumstances. So I'm going to start by just talking about consumer theory just a little bit. We have two models. The first model we did was the net benefit maximizing model. And we could do this in an abstract. And it was the benefits of Q. And that might vary with a person's income. And it might vary with the prices of other goods, for reasons that we kind of worked out in the past. At least always for other. And there's some cost to this stuff. And if we assume that this consumer is a price taker, then that's going to be price times quantity. And that will give us a net benefit for the ith person. And then we can take the derivative of that with respect to Q. And that will give us something like this. Right, so that first order condition will characterize the ideal quantity for this net benefit maximizing person if n is strictly concave. Okay, we can determine whether n is strictly concave with a contrary functional form by taking the second derivative of this objective function, net benefits, with respect to Q. However, with an abstract functional form like we might use, We basically just assume it. You can't prove it one way or another. When you do concrete functional forms, it's useful to check that second derivative, because sometimes I might do and give you a problem where the second derivative isn't negative, and the model will have rather odd properties in that case. And if I put it on an exam on purpose, which I might do, but it's not going to be the first type of problem I would put on there, of course. I might be just trying to get you to think through what happens when that assumption is violated. Now we can use the implicit function theorem to characterize this person's demand, and that person's demand is just Qi star. So if we look at these two, this expression here, that's a zero function, right? And the implicit function theorem says if you've got a function that has the value 0 and has several variables in it, then you can take any one of the variables in that equation, and anything that's in this part of the equation, and solve for any one of those variables in terms of the others, or at least characterize the relationship between that variable and the other ones. Okay, so we're interested in Qi star because that's I's demand curve, and we can write that down as some kind of function. I'll just call it QE for now. And that'll be a function of the price that is good, consumer's own income, and the price of the other good. We have characterized it right now. And we can take derivatives of that function with respect to price or income or the price of other goods using the implicit function differentiation rule. And to do that, we basically go back to the zero function, call that h, so we can kind of remember what we're dealing with. And then the Qi star, the E, for example, will be the h dp, or minus Qi, pardon, the h dqi. If you look at this equation, P is just occurs in one spot, it's minus 1. And if you look at the denominator in this particular thing, this is the derivative of the h with respect to q is just the derivative of n, the second derivative of n with respect to q. And so you could just write that down as the n squared Qi squared. And that's going to be negative if the net benefit function is strictly concave. Little minus sign out in front, so the whole thing is going to be less than 0. And so if the net benefit function is strictly concave, then it's going to turn out that demand curves derived from this function are going to be downward sloping. And that's true of all the functions that have this characteristic. Now in class I showed you how you can use geometry to deal with cases where the function isn't strictly concave. And we're going to get implications that are actually pretty similar to this in those cases, as long as at the margin, around the choice, around the Q star characterized by this, this marginal benefit equals marginal cost relationship, it will turn out that the demand curves are downward sloping for the most part. It won't be upward sloping, there won't be holes in the function, but there will be characterized by this kind of relationship. Because at the margin, the function, or in the neighborhood of Q1 star, the function is strictly concave. Now, the other thing we did was we looked at production. We used production as a source of information about a firm's cost function. And a production function looks kind of like this. It's some output that's generated by inputs such as labor and capital, and maybe technology. And we usually assume that this production function is strictly concave. And we also usually assume the technology is constant during the period of interest. We know that the cost of this output is going to look like WL plus RK, assuming the technology is fixed. And that means we can write, say, capital like that. So we can write Qj equals Q of L comma C minus WL over R comma T as our production function. And then we're going to maximize this output with respect to labor. And that will require the Q, the L, plus the Q, the K, times minus W over R equals 0 at L star. Okay, so we could write L star is some function L of the variables in the zero equation right here, and that's going to be, now we substitute out capital, so capital is no longer in the function. So we have technology and interest rates and the prices of the goods and C. So you could say C, W, R, and T. I think that's it, right? C, W is the wage rate, R, and T, L, and L is endogenous. And again, we could do comparative statics. We could take derivatives of this function using the implicit function theorem if we wanted to. But we could, at this point, characterize the amount of labor and capital being used, and characterize the cost function. So we could write this as C equals W L star plus R times C minus WL over R. That's a star. And so we would have a cost function, which will be some function of R, W, and T. Right, so by doing this using the implicit function tools, we get to a cost function kind of efficiently. Right? We just need to sort of think about the ideal quantity of an input, and certainly in two input production models, we can use a little substitution trick to kind of get at C a couple of ways. Now C is in this equation in two spots, right? So it's here and here. And so we're basically solving that relationship through this implicit function theorem. Okay, well, once we have the cost function, which is grounded in the production technology and input prices of the firm that we're modeling, we can think about the profit function, and that's just if this firm is a price taker, PQ. Uh-oh, I don't have a Q. Okay, so I goofed there. I have to kind of go back to that that process we were just using. Okay, so I've characterized L star, so I could write down Q star I is some function of L star, and capital determined the way we did it before, so K star, that's C minus R specify our W's R T. And then we use the implicit function here I grouped before. So we can use, we solve this for C equals some function of Q W R N T. Okay, so this, the other function would have been a cost function too, but this is the one we want. And we can use that in the profit function. The profit function is strictly concave. We can just take a look at this first order condition, and that would be P minus dCdQ equals 0 at Q star. So this is the profit maximizing output. And we could write down the firm supply curve. QS is a function of as a function of W and T and P. All right, so we can very efficiently get from the cost function after we derived it to the supply function of the firm. And again, you could use the implicit function differentiation rule to get at the derivative of that function. It's a little more complicated when you do it this way because you've got to do two implicit function differentiations because you've got to take those with respect to L, with respect to L star, and that requires going back to the other part of the derivation and using the implicit function theorem on that as well as on this equation here. So in this way, we get a supply and demand relationship in principle. Right, we know the supply function. So the market supply is going to look like this. It will be the sum of QJS J equals 1 to n. And that's going to be equal to the sum of QD I equals 1 to n. And this would be market supply, another market demand. And so we founded market clearing price. If we've managed to get those two quantities equal to each other, right? And P was a variable in each individual firm's supply function, and P was a variable in each individual consumer's purchase or demand function. And so we know that there's a P around there, and the question is, well, can we demonstrate for sure that such a price exists? And we didn't actually do that in this part of the class yet. We do a little bit more of that in the lecture on Tuesday. I'm pre-recording this on Sunday, so you haven't seen this, the demonstration that P actually exists. But if P does exist, and continuity of the demand and supply functions tend to assure that that's going to happen. They're going to cross somewhere in the domain of interest. And once you've done that, then you can use this setup to characterize comparative statics of the market equilibrium, right? So we can make H be equal to the sum of I equals 1 to n QD I minus the sum of J equals 1 to n QJS. And then we can take, can take a derivative with respect to any of the variables in that price function, in that price equation. Okay, and we use this relationship to characterize the equilibrium price using the implicit function theorem. And then we can take derivatives of this again using the implicit function differentiation rule. Okay, so in all these derivations, we were trying to point to a particular type of mathematical relationship so we can get back to this demand and supply characterization. And you have to remember that demand and supply curves occur. They are mappings from prices into quantities that firms produce for a supply function, and they're relationships between price and quantities that people with demand, in the case of the demand relationship. And when you go to the market, you basically have to add up all those supply functions for every firm in the market, or every firm potentially in the market, and also add up the demand equations for every consumer in the market, or every consumer potentially in the market at various prices. And that means if you take this in a very personalized way, as this formulation tends to generate, you're basically going to be dealing with a very long list of variables. Right? There's going to be n different income levels. There'll be the prices of substitutes from the demand equations, and then there'll be m input prices. If they're all buying the inputs at the same price, then R and W is enough. And if they're always the same or similar technologies, then you'll need one technology. But if they're actually working in different markets and they have faced different wage rates, they have different technologies and so forth, then you would need to list all of those different prices that they're making decisions based on. So we also dealt with the case where firms face downward sloping demand curves, in which case prices did not emerge from the same sort of impersonal market processes as they do in this sort of large-scale competitive type of model. In that case, each firm would set its own price or produce an output that would imply the particular price that it was going to sell its output at. And the only kind of market pressures indicated in that setup, or that in those derivations, would come from the demand function. So the demand function would include the price of other goods. The ones most likely to be relevant are substitute goods. And the better the substitutes, the more important the prices of those other goods are going to be in setting up this, determining the slope of the demand curves that individual firms face. So there's still some market competition in that model of pricing and output when demand curves slope downward, but it's not directly part of that story as far as we've developed it to this point. We also looked at another type of model where there's a downward sloping demand curve and there are relatively few firms in the market, and they produce perfect substitutes for each other. And in those cases, you could see how adding additional firms to the market would affect market prices and output. And generally, the more firms that you have in the market, the lower prices tended to be in that Cournot model. And the greater output tended to be, and it turned out that the closer market prices were to the marginal cost of production. And in that case, it turned out that in the limit, as n got large, the number of firms got large, that market prices converged to towards the marginal cost of production, which is the same type of price that we see in perfectly competitive markets. So in that way, the Cournot model provides a nice bridge between the monopoly type models and the perfectly competitive models that are at the heart of new classical economics. So on the exam, I will include a mixture of implicit function type derivations of the sort I just did today. And there will also be concrete functional form examples that will cause you to use the Lagrange. I'll try to pick out functions that are pretty well behaved, and so they should have fairly straightforward results. Occasionally I goof, and the setup I provide you with to work on doesn't have a neat solution. If you run into that problem, be sure to email me, and I can fix that and email back the whole class. So during the exam period, you should kind of keep your antenna up for possible emails from me that might modify questions slightly. I don't expect that to happen, but just in case, we have to be ready for the occasional slip that I might make. Unless the problem is right near the end of the exam, I think it's safe to say that any really complex aspects of the derivation were unintentional. The last problem or two, which will tend to be the most challenging on the exam, it's possible that I'll put something on there as a puzzle for you to work through that's not quite as straightforward. That's not a commitment on my part. I'm just saying that that's the sort of question I sometimes put towards the end of the exam as kind of a challenge problem. So with that quick overview of the class, as part one of the class, I think I'll stop this review and process this video and post it shortly. So I hope you find it useful. Remember that when you go through a recorded quick lecture like this one, you can hit pause. And you should take notes just like you would in class. And the way you take notes is you hit pause for a second so you can jot down a result, an equation, some remark I make before I move on to the next one. In class, I stop after I make a point. I look around the room to see if people are getting it or not, or whether they're caught up, and then I proceed to the next point usually. There's more space for writing in an in-class lecture than there is when I work on the whiteboard. So with that, good luck on the exam, and I'll see you when I get back, and I look forward somewhat to grading them. I especially look forward to it if they're all really solid, which I hope they will be. So take care. Thank you.